So I'm Sebastien Thuries from the CEA Leti in Grenoble, France, and my talk this morning is CoolCube through 3D VLSI alternative to scaling. As you may know, 3D TSV-based circuits are now in production side, taking advantage of what I call 3D coarse-grained 3D technology with TSV and micro pillars from 20 to 10 micron pitch. Okay, this take benefits of let's say HBM, HMC memory cube, and passive interposer. It's mainly for high-performance computing market. And what we can see is that recently Sony has decreased by 5 to 10x factor the diameter pitch for their three-layer stacked images here. So what we can see is that the 3D pitch of the 3D contacts are decreasing and quickly. And what we are doing next at Leti is what we call monolithic 3D. Also, actually, there are a lot of names, but I used to say monolithic 3D. It's also called 3D sequential. It's based on CoolCube process. There is a new program in the US called 3D SOC and so on and so on. It's always the same technology. It's a way to fabricate a second layers of transistor just on top of the very first one on a cold wave process. That's why we call this CoolCube. And this is a sequential integration, so that means that you grow your MOS just after the very first one. The advantage of this technology compared to the others is the high alignment precisions. So that's why you can use a 3D contact called monolithic intertier via with a pitch of a few hundred nanometers. Okay, so actually it's beneath 150 nanometers so far. Okay. At design level and architecture level, when we have a look to the literature and the state of the art, we have Stanford that has proposed brand new ultra vertical architectures to address the computing immersed in memory architectures and applications. They claim that they can reach up to 1,000 benefits thanks to MIVs combined with carbon nanotube technologies and non-volatile memory and so on and so on. On our side, we worked for the specific memory to logic partitioning for FPGA, showing some good results versus 2D implementations. Okay, and we will highlight in this pitch that regarding this technology specifically, we need to optimize the EDA tools that we have to get additional performance, power, and area gains here. So two messages here is that for huge PPA gains, think vertical, think really 3D from the architecture, and you need to upgrade your EDA tools elsewhere to have additional PPA gains at design level. Okay. So back to this 3D SOC in the US. Based on this works on Stanford side, the DARPA has set up a 3.5 years program to develop the technology. So I'm not going to explain all the program, but I just wanted to highlight two things here. The expectations are to clearly overcome scaling at 7 nanometers compared to 7 nanometer nodes. Sorry, with more than 15x, let's say, gain. And once again, there is a full contribution here to address the EDA tools. Okay. In this slide, this is the roadmap that we have and all the contributions we have on 3D designs and 3D circuits at the CEA. So I'm not going to explain all the roadmap, but we are going to focus on this last point, that is 3D VLSI, 3D monolithic 3D. Okay. So what we did in the past is a lot of contribution in terms of device silicon measurements and capabilities and so on and so on. And we are in a time slot where we have two MPWs, so two silicon MPWs defined here. And we are going to explore and to have a full overview of these two MPWs here. Knowing that for us, the objective is to follow the path of the in-memory computing cube, let's say the computing immersed in memory, very close to the memory, to address this bandwidth bottleneck to the memory. Okay. So what we are going to see through this presentation, some silicon device measurements, the last update of the silicon measurements we have at device level, sorry. Then we will see the specification of this both MPWs and the PDKit content and add-on and tools and object design in this PDKit. Then we'll make a specific overview of design methodologies for place route before having some concept and breakthrough in terms of architecture and the conclusion just after. So regarding silicon measurements, what we can say on the last measurements we made is that because it's done, because the second layers of the transistor are fabricated on the cold process around 500 degrees Celsius, it has a little derating on the performance, and we have worked to reduce this derating as much as possible. So far, the derating is about 5 to 10% from the high reference temperature. You can see on these both plots for NMOS and PMOS, NMOS on 5%, PMOS on 10%, and we are working to reduce as much as possible this derating factor with success. Regarding the MPW that we did a first one last year, end of last year, and we have a second one beginning of next year. We have two kind of PD kit available at this time. It's not big. Just to say that the first one was a pure R&D, CEA, Leti research here, and the second one is funded by a European project called 3DVLSI. Okay, so this is the route that we have defined. First of all, we are going to design the bottom layer on the baseline from STMicroelectronics 28 nanometers technology, and we are going to freeze the process to metal 4 here. Okay, so in that context, we have the full foundry capabilities of ST without any modification. Then the wafers are coming to the Leti, fabrication of the CoolCube MOS that are here. And with the contacts, we have the connection to the ground plane here because it's the SOI wafers. And we have the monolithic intertier vias that are processed at Leti. So actually, we can do 28 nanometers transistors, but the contacts are more 65 nanometers, so that's why the footprint of the standard cells is more 65 nanometers, leveraging a little bit the performance that we can expect here. But it's just a way to go to silicon. And we send back the wafers to Leti for the top back end of line finishing. Regarding the PD kit and all the tools that we have developed here, so we can start from the RTL or for custom design. You can go through all the toolbox to the GDS2, doing some layout capabilities, specs and extraction, DRC, LVS, full custom design, place and route, and also synthesis with all the classical EDA tools regarding this flow. And regarding the content of the PD kit itself, so as I said in the bottom die, we have all the design platform from ST, so that means that we have all the P cells for the analog side, SRAM and standard cells for the digital side. And what we do on Leti side, on top CoolCube die, we can do P cells, standard cells, and we have redesigned the I/O pads for the top die. So just one remark here is that the SRAM has to be on the bottom side. In terms of methodology, and especially for design level, so as we have already seen in the introduction, it's important to update and upgrade your design, because for, let's say, what I call coarse-grained technology, the major challenge was at, let's say, 3D advanced packaging level. Okay, you just have to connect through the interposer your CPU system and your HBM. So for me, it's addressing let's say, kind of global interconnect, and the job here is to do it at packaging level. Okay, when you decrease the pitch, you are going to shorten your local interconnect. So that means your design, place and route, and synthesis has to be upgraded at this step. Okay. Lot of contribution, by the way. Once again, there is a full DARPA program. There is a full task here. Georgia Tech, a lot of works from Georgia Tech, from CEA, from ARM as well, and so on and so on. So design flow needs to be upgraded for optimal PPA at design level. Okay. So here is placement standard cells, top standard cells designed in CoolCube process. You can see here all the standard cells here, and we can see here that we can easily put the SRAM memory just beneath the standard cell, having kind of overlapping of the memory and the standard cells. That's the motivation we have, is to use the classical 2D tools, the sign-off 2D tools, to optimize the result of the place and route design, okay? So the memory are placed on the bottom side. If we zoom a little bit, we can see that we have the standard cells that are placed, that are overlapping, the memory pins for power and signals, okay? So this is kind of 3D view, okay? 3D view of the 3D design. And what we can see here in the red dots are all the MIVs that are automatically controlled and managed by the tool for powering the memory, but also for the signals, as we can see here. And they are all placed in the free space between the standard cells. So it's a real 3D design here. Just take away for you, 3D VLSI design is now possible using sign-off 2D tools. We can take benefit of the full tier-to-tier co-optimization. I mean, the standard cells are placed accordingly with the placement of the memories. And this is what I call the optimization. And we can fully reuse all the 2D power mesh and clock tree and so on and so on. Just a word in terms of thermal, but I think that our friend from Georgia Tech will have a full speech here. We just made some experiments comparing these 3D technologies using the tool called Sahara from Mentor. We have defined a set of experiments with different technology parameters, number of layers, the pitch of the intercooler, materials, and so on. Different power scenarios, as we can see, for example, here. And we did the simulations to obtain this kind of plots with the results that there is better thermal coupling for hybrid molding and CoolCube. And it's very simple to explain and to see. It has some reduced hotspot effect. And there is strong sensitivity to interconnect and density and die thickness. The key is the die thickness. Thinner is your via, 3D contacts. Thinner is your die. So that's why you have a better coupling between your dies, okay? And thinner, smaller is the pitch. You can put a much more amount of 3D contacts to spread out the heat, okay? In terms of architectures, so we are going back as well onto this MPW contributions. But for us, like I introduced before, there is this specific link to logic and memory that we want to address. So that's why we have defined a first concept of on-chip memory cube. Actually, it consists of removing the bit cells array of the SRAM and to put it on top of the I/O, the control and redundancy in the word line drivers, and connecting it through MIVs, so we have no area penalty. What we can say is that we can have major footprint reduction of the memory itself. It's a plug and play for multi-tiers. It's toward NVM memory, we will see at the end. And in terms of number of backend layers that you need, you have reduced a number of backend layers used for connecting the bit cells array, because with 2 or 3 metal layers, it's enough to connecting it, knowing that this design can be reused as a plug-and-play concept, okay? And actually, this is the first contribution that we did at silicon level. This 2 tiers memory is here. This is the design in 3D, and this is in comparison the footprint of the 2D one. So the ideal results here are that we have reduced by 40% the footprint of the memory. We put, because it's a 128 by 188 for CT, 6 transistors bit cells, we have put almost 100,000 transistors on top CoolCube, reaching a high density, let's say quite high density here. The second test chip that we are going to do beginning of next year, it's full system on chip. So just want to say that we are going to use a RISC-V. Sorry for that. Very sorry for that, but it's very simple. It's because all the platform is already ready at RTL level, so we just have to work for the silicon. But for sure, if we have an opportunity to move for a Cortex or something, we will to show these results. And on the same road that we have defined, we are going to put all the data cache and instruction cache on the bottom on the bottom line, and then we are going to pull out the logics and the I/O pads on the top. So this is the, yeah, just one word to say that since it's not a true optimization of the technology here, what we are going to do is develop the full virtual 2828 PD kit to be much more aggressive here on the stack and to redo all the simulations for full 28. This is a contribution in the project, but also to have the same contribution. Now we have the background, the expertise, and so on, and we can do this for much more advanced node, taking into consideration that we are capable of extracting all the parasitics here and update all the libraries of the objects that are put in 3D. So just to conclude here, because I think I'm done. In this silicon and architectures breakthrough axis, we are here. So that means that we are frontier, we are pushing for the maturity of the technology up to achieving a full SOC silicon demonstrators, a full design platform for CoolCube. We are pushing the breakthroughs of our architectures up to ultra-dense in-memory computing cube. We think that it could be interesting also for smart imagers and smart sensors. This technology could be very helpful, knowing that we can take advantage of heterogeneous 3D integration to achieve multi-layer die stacking. Okay. Just next, and to finish that, to say that we have to push let's say device level. We need to align our thermal budget to support resistive RAM integration in the back end of line, and make some simulation at very advanced node to be let's say very competitive on for example versus 10 or 7 nanometers FinFET. Thank you.
Take questions from the audience?
Yes.
Yeah, so given that determining the worst case thermal gradient is a hard problem, it depends on the algorithm and also the input data. Once you do that, well, how do you do that first? And then once you do that, how do you mitigate the thermal gradient? Is it in the die, or are you using the package?
The question is about how modeling the thermal gradient
Yes.
in the study.
Yes.
Okay, so honestly, I'm not sure I can be very accurate on these answers. What I understood from the study made by my colleagues, that there is a natural spread about the heat that is 75% by the top through the package, sorry, and 25% by the active layers. Okay, so this is modeling into the tool.
So it's sort of more of a global model.
Yeah,
than
it's
application specific.
Application specific and global model.
And then how do you mitigate the thermal gradients? What's the general strategy? Are you using maybe redundant TSVs or conducting heat, or how do you get the heat out of the die?
Yeah, so this is what I explained, but maybe it was too first. The idea was first to when this, let's say, fine-grained technology appeared, everybody was afraid about thermal, saying, oh, look, with TSV we have very strong results, and so on and so on. So the idea was to first study the behavior with the tools that we had. So in terms of methodology, we in the roadmap that I showed, we have a full 3D design. We have chiplets on interposers. So we have taken this GDS, okay, and we have put this GDS into the stack, okay, and we have a lot of buttons to tune the materials, the number of 3D contacts, and so on and so on. And we can, this full cockpit is provided by the SARA tools that can monitor as much as possible your thermal behavior here.
Maybe time for one quick one.
A quick one. Yep.
What do you see as the fundamental limit to the number of tiers that could be made?
Number of tiers.
32, 64, 2.
So we did it up to four dies. I'm not convinced that you are going to put more in your realistic design one day.
Is there a fan-out issue with the interconnects, or is it just throughput time in the process?
I'm not sure to get
Why is 4 the practical limit?
Why is 4? honestly, 4 because, no, I'm not sure.
Partly because you cannot compartmentalize the design into heterogeneous layers that interconnect well? Or
No, that was not the motivation. We took 4 dice. It's just because of we wanted to study the number of vertical interconnects that we can have and the thickness of the die. So obviously, for example, in 4 die stacking, the 3 first are thin layers, and the last one is much more large layers. And for us, it's just a test case like an overrun, okay, just to study the thermal effect that you can have in your system. But there is no real motivation to put 4 or 3 or.
All right.
Okay,
Thank
thank
you.
you.